Okay. I want to share this link again. I'm trying to copy paste it. Yeah. Well, I hope everyone can access it. Normally, if you open it, you should see a window like this. And you need to log in with your own Google account. So I'll and then you should see the folder again. I don't know whether there's an option to give some feedback, like a thumbs up or so, whether it worked and whether I can go further. So
I've got it just fine. I'm following along so far.
might it be like I see people are still joining as guests or still joining the Zoom. Would you be able to share the link again, just to make sure they are being able to?
I'll do that.
Okay, cool, thanks. So whenever you're logged in, you can. I don't know how to. There's like, yeah, this little folder, and then you can make a shortcut to your own drive.
I just thought maybe if people are having problems or if they're a little slow or like if they're taking a little bit longer, you can just raise your hand. That way you can be more confident in like knowing that people are following along or knowing that people are having problems. So maybe if you have an issue, just raise your hand and we'll come to you.
Yes, because it's for me rather tricky to do this without any feedback. So you make a shortcut to your own drive. And then if you go to your drive, then you will see the workshop. And you can open it as a Google Colab. And this should run. So I run anyway. This should run, and I suggest just to clicking or running until you're here. Mamba, install Eelbrain. Make sure to run this cell as well, because installing Eelbrain takes quite some time. And then if this is in progress, then I jump back to the slides. So that's for you. I'm also going to open my version. Okay. Can they give some feedback on like give a thumbs up whenever it worked out for you? Like you have normally in the Zoom bar like reactions, and then you can give a thumbs up just to make sure that that people are following. Sometimes this happens. You see here the collab check, just run it another time, and then it will the error is resolved. I don't know, sometimes errors happen, unfortunately. Okay, so in my case, Eelbrain is installing. I hope, because I don't see lots of thumbs up, I hope everyone is okay.
Mine is still installing as well.
Okay, but still installing is fine, because then I would like to have the opportunity to quickly give some more details that I didn't have time to cover during the workshop. So using these TRFs or neural tracking, you can actually, or the goal is, you can actually go and describe the whole auditory pathway. And depending on the features or which features you select for your analysis, which is your, the thing you want to investigate, depending on your choice, you can investigate different characteristics up to the auditory pathway. And actually the TRFs gives you some additional insights. For example, fundamental frequency, which is thought to cover subcortically, have very short latencies. Envelope, the TRF shows later latencies. And then for linguistic processes or linguistic features, you see even longer responses. So the goal of this workshop is first to create those features that I use during my PhD, ranging from acoustics, sublexical, and linguistic features, and then also this subtraction approach. So we will start first with creating acoustic features, so the spectrogram and acoustic onsets. So creating these features takes quite some time, or also not only like your time, but also the computer. Sometimes it can be really heavy. So I will quickly open a repository, which I share at the end of this workshop, with all the codes to create these features. So because for example, the spectrogram, I have created the feature a priori, so we can just open it and look at it. But I want to quickly show you the code on how it works. Let me open the repository that I will also share with you. Okay. So hopefully you can successfully see this code. Yeah. Oh. I see a question from, yeah, okay, the Google Colab. Is it worked for everyone to, if you go to the, you can normally go here and then open with. And if you don't have this Google Collaboratory, you just say connect more apps, and you need to install the plugin for Google Colab. Okay, I hope everyone is like on the same page with me. I worry a bit that some people are lagging behind and cannot follow the workshop. But yeah. Okay, anyway, jumping from here to there again. So in the repository that I've shared, there's a create acoustic features. So basically, in order to create to create an acoustic feature, what you need is actually just the audio file, just the WAV file of the thing you presented. So this is the link to the WAV file. I saw in my slides that I forgot to introduce the dataset. So this is an open source dataset that we will use. It is our dataset of 85 participants listening to different stories or podcasts. And it's, yeah, super interesting because you have many different speech stimuli, and it's a very long protocol. So if you have multiple trials per participant. So definitely, if you have any cool hypothesis you want to check out, then definitely check out these datasets. So that's a dataset that I will use, or that I used in the repository that I will share with you at the end. way more details on which subjects were included and so forth can be found, so that you can really exactly replicate whatever I show here in the workshop. Okay, so we basically just need the audio file. It is not directly shared as a WAV file in the repository. It's saved as like an NPy, like a sort kind of data format from NumPy. But it's like exactly the WAV, so you can convert. You just need to write it out as a WAV to get it again to the WAV, or just download it via this link. Then you have the exact same. Anyway, so how does this do? How do you extract the acoustic features? To do so, I use the TRF tools toolbox. It allows you to first load a WAV file, then I filter the data, because our insert phones have a filtering function. Then I resample it just to make the computation time less. And then I apply a gamma tone filter bank. So the gamma tone filter bank is like a human-inspired filter bank, and you can say between which low and high frequency cutoff you want this, and how many channels you use. I typically just use 256 channels. But this is based upon previous literature, but now I just divided it by 2, because otherwise my laptop couldn't run this. For the spectrogram, so now you have the gamma tone spectrogram, which has a lot of filter bands, and then you group the filter bands logarithmically into, for example, 8 bins or whatever you're interested in, and then you apply the power law. And then we resample it to the original or to the same sampling frequency as the EEG. Okay, so now let's just visualize or go further in the work or in a collab folder and check how this TRF looks like, how the spectrogram looks like, sorry. I'm in between also looking at the chat. Is everyone looking, like, is it everyone working out to, most people are on track? Okay. So, okay, then just execute the rest of the cells. So here it will ask you to mount the drive. This is actually because within the folder that I shared, there's the data folder, which will call, where certain files will be called from from the collab file. So you need to allow it. You need to log in and so forth. And if you did that, then normally it should be mounted. You should get this message. This is important because here, some cells later, we will call the data. Oh, I observed that I still have the wrong name here, but anyway, you first import the packages, and then you need to copy. I'll also paste it in the chat. Change the root folder. Did that work for everyone today? Is the mounting successfully? Okay, great. So then we will visualize the acoustic speech picture. and if you run it, you should see something like this. So you clearly see like some sentences of this the spectrogram with at the different center frequencies, which looks nice. Another interesting speech feature to look at is the acoustic onsets. The acoustic onsets are the half-wave rectified derivative of the spectrogram. This actually accentuates all the edges of the spectrogram, and it's an important feature because apparently the auditory brain can respond or has a more prominent response to those edges than the spectrogram. So I always consider the acoustic onsets or acoustic edges as well. So like, as it's a hands-on tutorial, I also included some exercises. So the first exercise is to make the acoustic onsets feature. So it's basically you take the derivative of the feature and then clip all negative parts to 0. And to help you with this, check out the ILBrain documentation, because the whole workshop will rely on the toolbox ILBrain. And this spectrogram is already an ND variable, so an ILBrain object, so to speak, which has methods to take the derivative and to clip the negative parts to 0. I will give you some time. Meanwhile, if there is any question, or if you want to give any feedback on where you're at in the workshop, then please let me know. Just either unmute or put it in the chat. And then in a couple, like in a few minutes, then we can like fix this exercise. Yes, installing ILBrain takes quite some time. That's also like, if you ever want to install ILBrain, use Mamba. Mamba is really a time saver, because using Conda Forge or whatever, it takes quite a long time to install ILBrain.
Do these methods work in a similar way to MATLAB, in that if you have something with, I'm assuming the spectrogram channels are organized along columns, does it do the thing along columns?
Well, if you go to
maybe it's in there and I didn't see.
Documentation, and you, for example, want to take the derivative, then you can really say the dimension, and the dimension is really it's super straightforward. Time, frequency, it's in this case you want to use time as a spoiler.
You want to use what?
You need to take the derivative over time, and then you will have so okay, let's I'll make this first exercise. So you oh, I see there's an error. Yes, sorry, for the mounting stuff, I last minute yesterday renamed the CNSP_workshop. So in this one, data root. So you should rename it to this. If you replace it, the CNSP workshop with tutorial check 1, then it should solve. Brian, can you let me know if it worked out? And then we're... So back to the code. So if you want to take so we call it, when we make a new variable acoustic onsets, we use a spectrogram, and then we take the derivative over time. Next, you can also use the clip function, and it's you basically tell it like to clip all to clip at 0, so all negative parts will be clipped to 0. You can run this and then add another cell, and I can, for example, plot it. I'm going to take the same. So the sub function is it's basically telling them to take only like a very small part of the data, because otherwise it's a completely red figure, just to make it a bit more. Now you see it's way more sparser than the spectrogram, which is normal because like the if the spectrogram would be like this, the edges would be more like this. Okay. So yeah, in a next exercise, I quickly wanted to show you how the but apparently I already spoiled the answer. So to show you the relationship between the spectrogram and the edges. So if you just uncomment the first line. So either you can take the mean of over across a frequency like this. So mean frequency. Okay, so if you run this, then normally you can see the relationship between the two. So, Brian, so you changed the data root paths like this. And from then on, it should run normally. Does it work out for the other participants?
Yeah,
I hope it's working out for you guys.
It worked for me.
You might need to respecify other parts of the root directory name depending on where you saved it in your drive. So like I didn't save it in my drive. I saved it in a subfolder of my drive called Google Colabs because when I added shortcut, I needed to put it in another folder. If you use that.
Yeah, thanks. That makes sense. Good. Does that fix the trick? Anyway, if it's not working out, I will share like this will be available, the Google Drive will still be available until Leuven kicks me out. All the code is on my GitLab, so you will have the resources to replicate this. Okay, so then this is about the audio features. So basically we have the spectrogram, acoustic onsets, that's sufficient acoustic information. We went already to the code, so we can move on. And next up are the sublexical features. So basically we want to make this sparse array of features where there's a spike at every onset of a phoneme or word onsets. So basically, what do we need? To do so, you need to have a transcript. So you need to know the words which were spoken during the audio fragment. And also you need to have a text script file, or like it shouldn't be necessarily a text script file. It can also be another file, but basically it tells you when exactly a phoneme was spoken. So first, maybe a bit more on WhisperX. So you know this link. WhisperX, basically what you just should do, but we don't have time to go over it right now, but I give you all the tools. Just install this repository. It's very, very nice. And then the installation instructions are quite straightforward and well explained. So normally you should be able to manage. And then basically what I do is just running this line in command line, where in my case, this is NL because I'm using Netherlands, Dutch, and the name of my WAF. And then it will output you like this, and in the end, really a text file with all the lines which have been spoken, which is really, really nice. I know this tool only for the last 3 months or so. So the majority of my PhD have been transcribing a lot of stimuli. So this will save you crazy amount of time. So that's really, really cool. The thing is, it's super nice, but there are still mistakes in it. So just make sure you also do manual correction afterwards. Then secondly is to get that phoneme segmentation. And that's actually also not super difficult. There's like in my studies, we always used our own K Leuven stuff, but this BAS web service is also super, super cool. So basically, what you do is, I think it's another, you include the text, the output of the WhisperX. You also include the WAV file, you open them, you can upload them. And then basically, after it's uploaded and you changed the language to Dutch, which is the language of the WAV fragments, you can run this and it will output you the text file. This, like, yeah, I'm not going to do this right now because this again takes a couple of minutes, but now you have the tools to make your own text grid files, and you see it's not rocket science. It's quite nice and easy. Then again, if you want to go for it, then I also suggest you use Praat. I'm quite convinced lots of people know Praat already, but to make sure, Praat opens a window like this where you can really, if you open the text grid and the WAV file, which I'll do, so the text grid and the WAV file, voila. You can really open them together and you can really play around with all of this. And then you see in the beginning, maybe I'm quickly going to check whether audio is also shared. Yeah, I'm not sure though. Can you hear this? No? Anyway, here what I'm hearing is music. So here the segmentation is not done right. Later it becomes good. So just make sure you check your segmentations, your transcript, make sure to check them afterwards. For music, I would suggest to, for example, with Audacity, cut out the music to make sure your phoneme segmentation is done right. So as you see, making a transcript nor a text script file, it's not rocket science. So you can do it too. Okay, to the code then.
Hey, Marlies, before you go on, there is a question in the chat.
Okay.
So it's asking about acoustic onsets. Is there a recommended paper investigating the relation of the acoustic onsets with actual linguistic elements?
The paper that I would recommend is from Broadbeck. It's not necessarily related to linguistics, because linguistics is still a bit of a newer field, but the Broadbeck paper is super interesting because there they compared how you listen to an attendant and an ignored speaker, and what they see is that whenever an attendant speaker is masked by another, like an ignored speaker, or distracted by a distractor, then you can actually see that the acoustic masked onsets get unmasked in case they are attended to, but not in case they are ignored to. I hope this answers a bit of the question. I think I just want to highlight the importance. I think including acoustic onsets is really important because of this feature, but I don't know the exact relation with linguistics, because on the top of my head, I don't know a paper that's directly investigated this.
Yeah, okay, great, thanks. I know the paper, and I know that it is a commonly used feature, but I'm just actually curious, as with the many other features that we often use, assume correspondence to linguistic elements, but yeah, I would like to know better.
Thanks for your question.
Okay, thanks.
Marlies, do you mind scrolling up for just a second to get the end of that line? Yeah.
Yeah, sorry. This is basically the uncommented, it was in a comment, so you should just remove a hashtag.
Oh, that's silly. Sorry, keep going.
So yeah, then there's a really nice toolbox, which basically allows you to read in this text grid. So although I already made it as an Eelbrain, or I made already all features for you, but maybe it might be nice to make an ND variable ourselves. So basically, we're first going to load the text grids. So you have here where the text grid is saved, the path and the sampling frequency of the EEG. Then what you see whenever you load the text grids using the text grid toolbox, then you will see that you basically get an output of a dictionary with 3 keys. So you have the ortmau, you have the kanmau, and you have the mau. And in the ortmau, you have the words. So for example, if you do ortmau like this, you have a lot of intervals, and each interval still tells you which word has been said, and when the onset of that word was, and when the ending of that word was. So sorry. So to extract the word onset time, basically you loop over all these intervals in this ortmau element, and you just take x min. Sometimes there are empty words, really empty, so those you discard, because those are silences, and those you don't want to get an onset from. Then how Eelbrain works is you need to couple a lot of, or you first need to create a dimension before you can create a feature. So in this case, we're creating our time dimension, which is from 0 to the amount of samples that we require, and then the sampling rates that the feature should be. And then next up, we create the instance from all zeros. So we make a feature with all zeros, And then at the timing of the word onsets, we just put a 1. And then you can, of course, visualize this. So basically what I visualize here is the spectrogram, which is averaged across frequency bands, hence it's only one band. And then I also visualize the word onsets feature, so here in blue. So whenever there's a small peak here, there's a word onset. Okay, so next up, as a next hands-on exercise, I challenge you to make phoneme onsets. It's very, very similar to word onsets, but you should take the MAU instance, and I gave you already a hint that unknown utterances are given by these elements in the by the text grid. So I'll give you some time to make this exercise. And meanwhile, if there are any questions or issues still, then please let me know. Also, Brian, can you give me an update on whether it worked out?
When you, I have a question about the phoneme segmentation, the actual segmentation through mouse, and the manual changes. How exact would you say do you do this segmentation? Because we found that when we were trying to manually correct it, sometimes like auditorily, it's hard to find the exact boundary of the phonemes. And we do it, we separate between words, syllables, and phonemes. So we try to use the other boundaries to help us. But do you have suggestions about how maybe to improve on that, or is that just something that sort of rely on more like less exact?
Yes, that's indeed very tricky, because some phonemes they start rather silent, like or I don't know whether this is the correct example, but like you know, when you say hello, like there's no super hard edge at the beginning. That's indeed tricky. I usually do this together with colleagues who are audiologists and who are really trained in doing stuff like this. Yeah, it's also something that you learn through practice. It might be nice maybe to have a good reference system to make it more uniform, because yeah, I rely on how colleagues taught me to, and to do it a lot with colleagues who have way more knowledge than I have, because I'm not really trained to do this. I know it doesn't 100% answer your question.
No, it's good to know that everyone is in the same is in the same realm, like everyone's tackling the same challenges. Yeah,
hoping that you have a good phoneme segmentation tool like the bus services or so.
So we can't use the mouse because Hebrew isn't is not one of the languages that it offers. So we needed to find different methods to do this.
Yeah, previously we also used in-house a thing a guy created a couple of years ago, but yeah, it's always tricky when you're not English speaking. I feel hopefully the bus services have they do suggest something. They do have some suggestion on how to deal with languages they don't recognize, but I never checked that out, so I don't know whether it's worthy to spend time on to check that out. Okay, let's make this exercise. So basically, I'm just going to use same code. Somehow copy pasting isn't working for me. So basically, we want again all the interval. This time we only want the Mao instance. We don't want it to be at like one of these. Why is it?
I was also having problems with copy and paste.
Yeah, weird. Normally it's not such a pain in the ass, but I don't know why let's go a bit bigger. Syntax, because I shouldn't do the dots. Okay, and then we can create forming offsets. Ah, yeah, I can. Sorry. Yeah, nice. So I'll put the spectrogram average. Then maybe the word assets. I'll probably test first. Yeah, and maybe I'll immediately multiply them by 2 so you can see them. Of course, a comma. If you put another brackets, then they're all plotted on the same figure. So then you see the phoneme onsets, which are slightly higher than the phoneme onsets. Okay, cool. Nice. I hope that worked out for everyone. So yeah, we created now the acoustic features already, the sublexical features. So let's go quickly over the linguistic features. So basically we want now impulses with the amount of information for each phoneme or word. So first, a very conceptual description of what these phoneme features are before we're going to go really into the yeah, we're not really going to delve into the mathematics, so that's maybe good. So, but imagine whenever you hear the sound ba, there are a lot of words starting as well with a ba, and the idea is that our brain activates all the active words. And based upon these active words, you can actually calculate, for example, the phoneme surprisal. So how likely the B is in this whole cohort of words, or you can calculate the cohort entropy. And this is actually the Shannon entropy. So basically what this formula is of these of the compatible words in the cohort. It's basically the degree of competition. You should see this if there are a lot of likely words, if in the cohort of activated words are lots of words which have a high word probability, then the degree of competition of which word it's actually going to be is high. But if the cohort, if there is only one item which has a high probability and all the other items are fairly low, then of course you have a low degree of competition and your cohort entropy is low. The general trend of these phoneme features is in the beginning, the first phonemes in a word have high phoneme surprisal and cohort entropy. And the more towards the end of the word, the smaller the value becomes. That's the general trend of how it works, because then you have a better prediction on what the word is actually going to be. For example, if I tell elef, then you are probably aware that the word is going to be elephant, and the last phonemes don't really matter that much. In my studies, I always computed it using just the word probabilities of the standalone word. So independent of the context of the previous words. So the code that I share with you is also using the word probabilities of the independent words. So in order to create these linguistic features, we of course need a pronunciation dictionary. A pronunciation dictionary is a mapping of a word and how the word would be pronounced. So to create this, to create a pronunciation dictionary, you again have this bus tool. There is the G2P, and basically you just input a file with all your words where you want a phoneme segmentation from, and inputted it here. So based upon my previous studies, I always use the word frequencies of subtelex. I think I also have a slide on this. Yeah, here. So I use the word probabilities on subtelex. This is also available in lots of languages. Not sure whether it's available in Hebrew, but anyway, any word frequency measure that you have will work for this. You just need to extract it another way. So basically what I've done in my code is first to take the words from subtelex. This is a very stupid script, but it reads in subtelex, and it just takes all the words and removes some which are very infrequent, because often there are very weird words that I've never heard of or have very weird symbols in it, just to clean it up a bit. And then there is a maximum amount of words per file that you can insert in the bus web application. So then I just write multiple files, and then basically I have let me open the directory again. I get these subtext words, and that's then the file which I insert in this pass tool. And then after a couple of minutes, it gives me this this file where you have a word and then the phoneme segmentation. So yeah, so based upon this, you can basically go ahead and compute word surprisal and cohort entropy. If you don't want to do all the mathematics, or I wrote these functions which you can find in the GitHub repository, that you can use to calculate your own phoneme linguistics. But for now, yeah, I don't know whether I should. But for now, for this workshop, I just provide you the outcomes of these models, because also creating these like phoneme calculations, for example, it takes me like it takes almost a full night before this 15-minute long audiobook is fully that I have the phoneme linguistics for this audiobook. So it takes a while. So it's not possible to do this during this workshop. But now you have the code. Then at word level, so this is the example from previous. So at word level, I use word surprisal. So basically, it's the probability of a word given the four previous words. To do so, I use a simple n-gram model. Unfortunately, I haven't found a way to share it with you yet because it's 2 GB and it's a bit too big to share. But if you're interested in the Dutch version, then just send me a message. The word probability is just, yeah, the probability of the word. So as I said, I use an n-gram model. This is, yeah, a fairly simple model, and to create this, I use the GenLM toolkit, where you can write, yeah, the GitHub page it's pretty yeah, extensive on how you should train a language model, and it results or gives us an output, an ARPA model, which you will use to estimate the word probabilities. So in the file here, I think. So you load the ARPA model, and then you can really, using this ARPA toolbox, you can just get the word probability with this very simple line of code, or the probability of a word given the previous words. But those I already created because it takes a while to compute these features. But we can look at them and load them. So here I show you the phoneme surprisal derived from subtext, and then I challenge you to just load in all the other features. So you can see how they are named. If you open stimuli, then you have all the features. Basically, just writing. I will entropy. I hope you can rename it too, so you can. Ah, damn! I'm not going to be able to paste. Oh, this sucks. Life is hard. Is everyone having copy paste issues? Because that's pretty weird.
I'm not able to right click copy and paste, but I can use the control C and V on the PC keyboard just fine.
Because that doesn't work either for me. That's a bit. Yeah.
I think it's word surprisal and gram.
Yes. Sorry if I'm keeping you guys up. Okay. And then let's plot them into each other.
You chose the same thing for the word frequency, word surprisal.
So I'm gonna add an offset to each. So +2, +3, 4, so we can see differences. If I have spelled stuff correctly, of course. And then you see how it looks like. Yeah. Good. So now we have these features. Then I want to just quickly show the slide like before. So basically now to assess the added value, we just need to create two models, like a complete model and a baseline model, where one has all features and one where we have all features except for the linguistic ones, and then we take the difference between the two. As a quick note, the ill-brain toolbox uses boosting, so this is not the same as we saw in Ole's talk. So it doesn't use retrogression. to quickly explain how it works, so basically it fits, it estimates the TRF first by flat line, and then it's basically at each sample of the TRF, independent of, like at each sample of the TRF, it starts predicting the EEG using a small increment size, and it sees how well the model performs. Then it does it with the next sample, it puts a small increment on it, it sees how good the model performs, and that it does for all possible samples, positive increments as negative increments, and then it detects which increment on which sample the model performed best. Then it puts the small increment on that spot, and basically then the same process happens with this as a baseline. So basically then a new increment is added and fitted on top of all samples, positive and negative, to see where this increment is best placed on top of this one, or maybe here a negative one. So it's a different procedure, it's an iterative procedure. So just to keep in mind that it's slightly different than what Ole explains. So here, first I just take one subject, the EEG of one subject, and I make an ND variable from the EEG. To do so, you need also a sensor dimension, which I created here, so that ILBrain knows that it's a sensor dimension, that it has a sensor dimension and a time dimension. Then you estimate the model by calling boosting. Here I limited the EEG to, or I just used 3 minutes of data, because fitting a model takes some time. I start from 0 milliseconds and I stop at 500 milliseconds, so 0.5 seconds. This is the basis function. The basis function is basically the kernel that you convolve the TRF with. So basically you should see this as these are all very small spikes. And the basis is like a kernel that you convolve with this window, so all those spikes becomes a little bit broader. But yeah, so let's run this. This should take not super long, but takes a bit. I hope that's working for everyone.
What does that basis value represent? Standard deviation, something like that?
It's also a time, the width of this of this kernel which you convolve it with.
Cool.
But there's a small exercise here where we will play with the width of the basis, and then you will clearly see how it affects the TRF. The basis function, like it's a definition of the kernel that you convolve this spiky TRF with. And if you want to go into more ILBrain stuff, you can also say which kind of window this should be, whether this should be a Hamming window, which is the default, or a Gaussian or whatever. So yeah. Does that completely answer your question?
Yeah, it does. Thanks.
Is there something that you do when you input the different features to account for the fact that the acoustic envelope is at a different scale? Like, do you scale the different features to the same scale?
Boosting does this. Boosting normalizes the features.
You don't do this outside, like the toolbox does it automatically?
Yeah, in the boosting function. You will see later on, or if you're playing with the results, you have an H and an H scaled, and counterintuitive, the H is the scaled one. So when everything is normalized, and the H scale is, if I'm not mistaken, the not scaled one. So if you want to assess the effect of so I hope the boosting models ran for everyone. So you can visualize the prediction accuracy by running the next cell and the TRF. So those two important outcomes of the forward model, like this. So this is just one subject, fairly high prediction accuracies, which is probably just due to a lucky shot. And then the visualization of the TRF, where you see this peak-ish around 200 and like a peak around 200 milliseconds. So then we're coming to the exercise to play around with the basis function.
Sorry, I don't know if I missed it, but what did we include in this model?
This is really just running one forward model. So we have here the spectrogram. So this is the EEG and spectrogram. And we start at 0 until 500 milliseconds. That's the window of our TRF from 0 to 500 milliseconds. This is 5 partitions, so meaning that we divide our data in 5 equal parts, where you use here 1 partition for testing the model and 4 for estimating the TRF.
And your data set, you said, is just a 45-minute
yes, but we here we just load 1 subject and we just take the first 3 minutes.
Okay, so those 3 minutes are divided into 5.
Yes. I can here plan to show a bit more details on how this partitioning works. So, okay, so we have the prediction accuracies and a TRF. So let's play with this basis function. For this, I will just limit the time for training now until 1 minute, because using only 3 minutes takes already quite a long time. So yeah, here I will just give it the start and stop any amount of yeah, I can copy paste. This starts here. I will disable the testing partition just so it takes less time. Some more people. out whether this works or not. Nope. Yeah. So please. Um, good. We also need to take the new book this semester. Something essential because I didn't include my basis. Sorry. This is a stupid error. Okay. Is everyone still a bit following-ish? Okay, hopefully now it works. Voila. And now you see that for longer kernel, maybe I can zip the basis names. Yeah, let's not do this because otherwise I lose time again. But for the long basis window, you see that the TRF is very, very smooth, and depending on the shorter your basis kernel is, the more sparse your TRF becomes. I generally use 50 milliseconds basis function, but this of course depends also on your sampling rates. I generally use 50 milliseconds for 128 sampling rates, but for 60 it's probably better to check out a different basis. Yes, so the kernel simply, yes. Like in these cases, it will be just nearly an impulse. If you go broader, then it's more like, yeah, in this case it's a Hamming window, but think of it as a bit of a like Gaussian, but it's not a Gaussian, that it's just smooths out all small nitpicks. Okay. Yeah, so basically, I would like to challenge you to make basically the same model, but then next to the spectrogram also includes phoneme onsets. And then we can investigate the added value of phoneme onsets. Boosting, so we can take 3 minutes. And this time, so then you include it as an array, the spectrogram. If there are any questions meanwhile, then please let me know. Yeah, I need to check out how I code it again. Sucks. Oh, where was I talking? Well,
So there is a discussion in the chat about what is this basis kernel exactly.
Yeah.
So, and then wait. So Andre is asking, so the basis parameter specifies the width of a Hamming window, which is the kernel,
Yes.
correct?
Yes. Yes, and then you do this convolution, so this multiplication over time to have your speaky TRF into something way more smoother.
Okay. Thank you.
And then we run it with the same specifications, which was I see. For what reason would the TRF be smoother? Sometimes it performs slightly better when it's smoothed, because, for example, you will have due to training peak, like lots of peaks like this, and due to smoothing, your peak will look like this, and that might slightly improve the testing on the testing partition. Additionally, why you want to also smooth a bit is just to allow it to be more generalizable across all participants. Because if you work, for example, with a very sparse TRF, for example, let's say that it's for subject 1 like this, and for subject 2 it's exactly the same but opposite, then the average, yeah, okay, maybe a bad example, maybe subject 2 should be a small peak straight next to it, then the average TRF would look with bad color selection, would look like this, while in case you would have smoothed it both peaks a bit broader, then it would be maybe like this. Is that clear? I hope it's clear. Okay, so I think I use a basis function for coefficients.
I have a small question.
Go ahead.
Here in this line that you're doing this
Yeah,
model?
sorry, I'm quickly checking whether my arguments are correct. And then,
It says time equals 0 to 180, and on the one before it says none to 180. Is there
yeah, I don't wait. In the one before it says none. Where does it say none?
here in the one that you were looking at before here?
Here.
No,
one.
down more in the boosting model. Yeah, here.
Here. Because the first sample will be none. So then, because this sub takes basically a subsection from a point up to 180 seconds, and either it's none, meaning saying like just take up to this time. For example, if I would have, if I had a TRF from -100 to 300 milliseconds, and I would say time going from none to 0.3, then I would get from -100 to 300 milliseconds. If I would do 0, then I would only get the 0 to 300 milliseconds. But now, yeah, EEG and spectrogram both start at 0, so it will be the same.
Okay.
It's more like the first sample of whatever you're indexing there.
Yeah. Where's the error? Here, I guess. Should have been able to copy paste stuff which specific. Here is an error.
It might be the browser. Or something about, I don't know what browser you're using, but something says that it doesn't.
Yeah, it's weird because previously it worked out, but now it's acting weird. Anyway, it doesn't really matter. As long as you bear with me and me struggling and typing typos, and that's okay. There you can see like a frustrated coder in front of her laptop.
What does the end of that code say?
So basically, I again set the basis window, the amount of partition, and selective stopping. Selective stopping is actually, so when you have this algorithm, it is iteratively, so it will basically never stops unless you tell it to stop. And this says like take the stopping criterion L1, so it's that the error should be based upon the, oh no, I'm sorry, I'm messing up with a different argument. This is saying that after that one iterative step increases in error, so the prediction becomes worse, then you should stop with the fitting of the TRF.
Makes sense.
About the L2 and L1 stuff, you can also have an argument error. So I was a bit caught up or mixed between. So you can plot the prediction accuracies of this R2 model and how the TRF of the spectrogram looks and how the TRF of the phoneme onsets looks. By the way, these effects here, as a side, these are edge effects, and these generally occur whenever your TRF is trying to explain something which is happening outside the boundaries of your integration window. And that can happen. I would suggest to increase the integration window here, or sometimes with adding multiple features, these effects disappear. I would really suggest to increase your integration window, so the T start and T stop, especially when these effects are prominent on group level. Subject specifically, it might be still a bit noisy and stuff, but yeah. So here you plot the topo butterfly, and you can set the timing of this topography using the T arguments. So then let's together determine the added value of phoneme onsets in this case before we do the or go on to the next step. So
I have a question.
Yep.
Our plots are very similar but slightly different. Is there like some randomness built into the boosting algorithm? Like, does it
Yeah,
like
well,
sample?
Normally it should be fairly similar.
Oh, it
And
is. It's fairly similar. It's just there's, some really subtle differences. And I'm just curious if there's like any like optimization or randomness built into it. I just don't know how the boosting algorithm works.
Yeah, not that I'm really aware of, unless there is change, or there something has changed lately. That's a bit weird though.
I mean, if it was just choosing at random, say, let's put an impulse or let's put a kernel here, does that help? No. And then randomly,
Yeah, but it still then decides which one is the best one, and that should be, in my case and in your case, exactly the same.
what if, but if it starts off with, maybe the first couple of steps that are slightly different and they all like add some value, at least at the beginning, things can be adding some value.
Yeah,
Maybe like it goes up on slightly a different tree. I mean, it's very similar. I just like, for example, the low V at the far left has a few other like lines that are close by instead of the big gap. But I mean, like otherwise it's like almost exactly the same.
Yeah, I'm not completely sure, because, for example, how large this peak is
Yep.
set and so on, those are all defaults normally. But probably if it's slightly different, then probably there should be some small randomness in the code, but I'm not sure where it is introduced.
Okay.
Like on the top of my head, I didn't think so, but maybe I missed something in more recent versions or so. I don't know.
No worries. Maybe we'll ask Christian.
Yeah.
Could you send the last code for the last model? There seemed to have some kind of error, and I'm not sure which one.
This one, yeah, I can try to copy and paste it. Great. Thanks. So basically you just take the prediction accuracies of the second model minus the I hope I called it R1. I'm sorry. Okay, I called this one RB. Whoa, nice. So that we can take the difference. So hopefully this works. And then we can visualize the topography using the Ilbrain topo plots. Topo map it's called here. And our and then these are just some arguments that we really use to make it more beautiful. You shouldn't, but I like to nice or maybe spots message. Voila. We can also plot the additional color bar. What's color bar? And then you can say difference in prediction. Whoa, that's really high for a difference in prediction accuracy. Let's double check. But probably it's just because the values here are so crazy, because it's situated more here. So if you can set the max, for example, for this, probably clear where the added value is situated. Okay. So that's basically how to calculate the added value. Here, I just wanted to give you additional, like just to yeah, have some feeling with this segmentation stuff. So in this case, we use 5 partitions, and if you don't use the test argument, so if you do test equals 0, then you see that Brain basically, before it starts testing the model, divides your data in 5, uses four partitions to train the model on, and this is for validation, so to determine when the fitting needs to be stopped and to apply this validation of the model, and to determine when the fitting of these increments should stop. If you use a testing partition like this, then you see that there are way more splits and that it also takes way more time. So then you fit a model on 3 partitions, use 1 for validation, and then apply the model on this fault. If you plot the TRFs, so the R.H, then you obtain the average of all splits. Okay. Is that okay for everyone? Is everyone still a bit on the same track?
Could you scroll up a little bit to where you did the difference in the prediction accuracy?
This part?
Yeah. So what we do here is but R2 was the
R2 is the model we trained the last, with including the phoneme onsets.
So it was the combined one of the phoneme and the...
And then we subtracted the spectrogram, so we have the added value of the, well, what did I do here? We have the added value of the phoneme onsets. Okay, so will there be answers to the exercises? Yeah, sure. So I will save this file, and then whenever you open the document again, you will have the file with all answered exercises. So no worries. And also I will give you a link to the GitHub repository so you have all the code. So now I want to show how the linguistic features actually look like. So basically we have all the tools, we have all the features, we know how to estimate a TRF, to compute the added value that we just did for phoneme onsets. Now we use exactly the same pipeline, but use it for the linguistic features. Because this takes a crazy amount of time, because you do this for 15 minutes, lots of subjects, and yeah, you have lots of features in the model. This takes quite some time. So I already, I'm quickly going to make sure you don't hear the background. Okay. So I will show you. I pre-trained all the TRFs already for all subjects. So for every subject, you have a complete model, and you also have a baseline model. So basically, we will just load in the complete and the baseline model for every subject, and we'll do the difference between them. Note, yeah, this is exactly the same outcome as you got in the R instance here. So. Okay, so basically this calls the TRF directory that I just showed you with all the pre-trained TRFs, and then it loads it, and then puts it in a row to make an brain data frame. So if you show this instance, then yeah, it has the subject name, the model type, whether it's complete or baseline, and then it also has an ND variable called prediction accuracy. So then using Topomap, you can really easily use this data frame to show the prediction accuracy for each model. So then you see on the first side, you don't see a clear difference between the two models. Then using statistics, which is really handy to use the ill-brain toolbox for. So if you do the t-test related, it's not a actually it's a permutation test based on Marlies and Oosterveld that will be applied to test whether the prediction accuracy is significantly different between the two models, and it says like use the matching factor subjects. So if you run this, oops.
אני מנסה לעקוב.
Sorry?
בשעות האלה של הלילה אני לא יודעת מה באמת נספג, אבל...
Okay, so then you can see the difference between the two models. So here in the we know there's a significant difference because there are these curves, but the color bar is way too broad to actually visualize the difference because the added value is small from linguistics. So if you do res mask difference, you can actually plot it better. And then you see in blue, because it's baseline minus complete, and the complete model has the added value of the linguistics. So the complete model is higher as a baseline, so the difference should be negative. And then you see that there's a prominent improvement here in central areas of the brain, where we expect that linguistic features have an added value. So yeah, to maybe it's not yeah, super interesting because we know that there is a significant difference between the two, but just for sake of exercise, we will make a new data frame with the difference. And then we can plot it right. So that's nice, I guess. So we look over all the subjects, and then we take the complete well, I'm working this. I'm sorry if you're typing exactly the same as I am doing. I write a lot of mistakes. So we want the subject to be the same, and then the prediction accuracy should be of the heat model. And then this, and then I like to use a lot of assert functions to make sure that it's the right it's how I expect it to be. So I expect only one correct entry corresponding to this line of code. This time we want row No, it's right. Let's see. Baseline level. I don't know what I'm missing here. Probably the errors later will tell me. Let's check out all the errors. Okay, so we have our rows, and then we need to make it into a data frame. Yeah. Okay, and let's show the total map. Okay, so this is what you expect. It's very similar to what I've shown above. So if you want to make it more beautiful, you can let these arguments, which I like. Voila. Okay, beautiful. Yeah, last minutes. I hope I didn't include an exercise. Anyway, yeah, I did still. I'm sorry, maybe I made it too intensive. Anyway, this is to load the TRFs. We can also just quickly go over it. Basically loads again the TRF. I only look at the complete model because that's like what we're interested in. If the ILBrain requires in a data frame that the ND variables saved in the same column, so to say, to have the same dimensions. And because the spectrogram have the frequency dimensions and the, for example, the TRS for word surprisal don't, I take the average across frequency to make a nice data frame. So here again, the TRF of the spectrogram. Then, yeah, how to use this sub channel selection to take the mean of a certain channel selection. So this channel selection we defined earlier, it's this here. So these channels, and then you see that if you have like lots of participants, that you have really a very beautiful TRF with P1, N1, P2. Nice. This is also a nice function if you want to do cluster-based permutation tests. Cluster-based permutation tests to see where the TRF is significantly different from 0. So this is currently running. Meanwhile, I'll type the solution of the last exercise so that we can still have a quick chat. Maybe if there are additional follow-up questions. So basically, here you see whenever it's colored, the TRF is significantly different from 0, and especially if you have lots of participants, this is quite prominent. You see the gray that for some channels, sometimes when it's very close to 0, it's not significant. Okay. Maybe I should just do 2 features for sake of time. Okay, yeah, could have included all of them. What did I do? Probably I misspelled something. Subtext. So yeah, so maybe also set the title to the feature. Here we see both the feature of cohort entropy and word surprisal. This is rather a subtle effect, and here this for me, because this is for me the first time that I tried this in this data set. Normally we expect this effect slightly earlier, but now I created linguistic features using a completely different corpus, so maybe that does the trick. Maybe this also slightly occurs later, but it will be a bit of playing around with it. But again, as expected, linguistic features, they have this characteristic topography. Yeah, as expected. I think for sake of time, I'll stop here. I'll add some more codes later to show this in one channel selection and to do statistical testing and to see whenever the TRF is significant. But I'll add that so you will have that as well. Just to end this workshop with, I'm sorry that it went super fast paced. I expected that it was more chilled, but anyway, somehow I slightly prepared too much. If this overwhelmed you or so, then and you have further questions, really don't hesitate to contact me. Here you have my email address. You can also reach out to me on Twitter. I have put all my code on my GitLab. I think you should be able to find this. So basically it's this repository, so you can generate everything from scratch. Also, I try to document the code and my steps as good as possible. But if you still have questions, then don't hesitate to ask them now or to reach out to me later. And it's a bit sad that online. It's also really cool that that you can all participate, but I wish we could have a chat together. I could see your faces and maybe grab a beer or so. So if you ever at a conference and I'm there too, then please come and reach out, and then we can have a beer together.
I'd have a beer.
Me too. Thank you very much. So there is any question?
I have a few.
Go
It sort
ahead.
of it sort of has to do with what you were saying about channel selection. In the data that you presented earlier today, do you usually do some kind of cluster of, like, do you look at a specific cluster of channels? Do you just look at what is significant above chance? Like, how do you usually make that selection, and how do you prevent sort of the multiple like when you do the statistics, the multiple test
Yeah. So I think there are two proper ways to set channel selections. And either it's a priori, like even before you start processing your code, by looking at what previous studies looked at. So because like you should set your channel selection in an unbiased way, so to speak. If you look at the prediction accuracy, see where it's significant, so on, then you're actually already biasing your TRF analysis on where it will be significant. If you want to bypass this, I think you can also, but then it's super nested cross-validation wise, just to really test the prediction accuracy where it's significantly higher than 0 in one partition where the data is unseen, and then test that on the TRF. But that's very, very nested. So I just like to stick with a priori channel selections.
And that brings me to another sort of topic that wasn't really discussed a lot in the workshop in general, but our lab started using the RCA method to sort of filter the data before into this sort of components, and then we sort of run our TRFs on those components. Do you think, like, what have you had any experience with sort of those methodologies? Do you have any thoughts about that?
So I only use this using principled component analysis first and then applying TRFs, or first estimating TRFs and then applying PCA. Because then in a way you do your channel selection already, which is nice, right? Because you only have one component. Depending on which component, like how you go to the components, which method you use. I use PCA that I set, or not for any projects that I presented now, but previously that I set subject specifically, and then especially for acoustics, the first component will be super similar across all participants, and then I think it's safe to use, in case of PCA, polarity, the sign is arbitrary, so you just need to make sure that all the signs are flipped. But except from that, I think that's a very valid approach to do as well.
Thank you.